Hi everyone, we're going to talk about two tests today, the direct comparison and the limit comparison test. So the direct comparison test is really convenient. It states that if we have some summation that converges, okay, and this summation is bigger than whatever we're comparing it to, then that means that the smaller one will also converge. Okay, and if we have some summation that diverges, and this same summation is smaller than another one we're comparing it to, then that second one will also diverge. Okay, so what I mean by this is, like how we use this in practice, is say, okay, so I'm given the summation of 1 over n cubed plus 1. Now what I'm going to do is compare this to a summation that I know the convergence of already. So I'm going to compare this to 1 over n cubed. So essentially I'm simplifying the function that I have. I'm taking away all the extra numbers, any coefficients, I'm taking those away, stripping it down to bare bones. I just have 1 over n cubed. I know that this is convergent because it's a p-series with p greater than 1. Okay? So the convergence of this is very easy to identify. Now I'm comparing this to this, okay? Now because we're working with fractions here and I'm adding one to my denominator, that means that every term of my function here is going to be bigger than every term here, okay? So, I mean, if you get kind of confused about that, just plug in some numbers, okay? If I plug in 1, I get 1/2. If I plug in 2, I get 1/9. If I plug in 3, I get 1 over 28. Okay, if I plug in 1 here, I get 1. If I plug in 2, I get 1/8. If I plug in 3, I get 1/27. Okay, you see how every term is larger in my second term? Okay, that's what I mean by this summation is bigger. Okay, so I'm going to compare these. Now I'm going to say that this is bigger than the one that I'm given. Okay, I know that this converges. Okay, I'm going to write that a little neater, sorry. I know that this converges because it's a p-series with p being 3, which is greater than 1. And because my comparison series is larger and it's convergent, that means that my given also converges. Okay, so basically if your larger series is convergent, that means that this one has to converge to something. Okay, and if your smaller one is divergent, well, if you're and your second summation is larger, well, if you're bigger than infinity, then you also have to be infinity, so you're also divergent, right? So that's kind of what we're going for here. Okay, in our second one, I'm going to compare this to the sum just 1 over 3 to the n, so I'm getting rid of the plus 2. Okay, now this is a geometric series where r is less than 1. Okay, where the absolute value of r is less than 1, it's 1/3. Okay, so I'm comparing this. This is larger than my given sum. And again, if you get confused about that, plug in a couple numbers and see which one starts off bigger, all right? But I know that this is larger because my fraction is going to be smaller here, so it's going to be larger. Sorry, my denominator is going to be smaller, so my numbers are bigger. Okay, so I'm picking a larger series that I know is convergent. Okay, so I see that my comparison series is larger. I know that 1 over 3 to the n converges because it's a geometric series with my ratio equaling 1/3, which is less than 1. So therefore, I can say that my given my given series, 1 over 3 to the n plus 2, is also convergent. Okay, and you could say by the comparison test if you wanted to be thorough. Okay, by the comparison test. All right, one more example of this. Here, you can probably guess what we're going to compare to. So I'm going to say that this is less than, this is greater than the summation n equals 4, and then just 1 over the square root of n. Okay, and again, if you plug in a couple numbers, you'll see that this summation that I chose is smaller because my denominator is going to be larger. Okay, now what I chose is a p-series. And my p-value is 1/2, which is less than 1, and therefore this summation is divergent. Okay, and because my divergent series is less than my given series here, I can say therefore my given series is also divergent by the comparison test. Okay, so those are some examples of the comparison test. Now we have something called the limit comparison test. Right? And the limit comparison test is pretty good. Okay, we can talk about in class like when you would do either one. But hopefully maybe look at the difference between some of these examples and the ones that I just gave you and see if you can do the limit comparison test for those and see if you could do just a regular comparison test for these. Okay, which more or less you can. But here, what I'm going to do is choose a function. I'm going to choose 1 over n. Now that might seem kind of arbitrary to you. Now there's two ways of thinking about this. Okay, because here's what I'm going to do. Whatever my function is, I'm going to take this and divide it by another function that I'm choosing. And the function that I'm choosing should be something that I know the convergence or divergence for. Now I'm choosing 1 over n, first of all, because I know that this is harmonic and it's divergent. I'm also choosing this because if you take this and you simplify it down to bare bones, you get rid of everything else. You get n to the 4th over n to the 5th, which reduces to 1 over n. Okay, that's one way of thinking about it. Or I'm choosing something to the point where, I have n to the 4th and n to the 5th. I'm going to be dividing by this. And I want something that will make my top and bottom powers be the same. I want the degree of my top polynomial and my bottom polynomial to be the same. Now, if you kind of go through this simplification technique, then it'll always work out for you. Right? So essentially what you're going to want to do is if you have a lot of terms, you get rid of the extra terms of lower degree, and you get rid of any coefficients. You just take those variables, simplify it, and that's pretty much the function that you're going to choose every time. Okay, so in this case, I had n to the 4th over n to the 5th again, which reduces to 1 over n, so I'm picking 1 over n, which I know is divergent. Now what I'm going to do is take the limit as n approaches infinity of my given function divided by my chosen function. Okay, and what ends up happening is you end up multiplying by the reciprocal. So I'm multiplying by n over 1. All right, so that's going to give me the limit as n approaches infinity, n to the 5th plus 10n over 4n to the 5th minus n cubed plus 7. Okay, now when I take the limit to infinity, all I care about are my coefficients of my terms with the highest degree. So I don't care about any of this stuff. I just care about this. So my limit to infinity is going to be 1/4, right? And so if you get an answer here, essentially, if you get some number, so as long as you don't get infinity, that means that your function will behave like your chosen function, okay? Or this series will behave like this series. Now this series diverges. I know they're going to behave the same because I got a good answer here. So that means that my given series will also diverges. Okay, so I know that 1 over n diverges Therefore, my given sum, so n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7 is also divergent by the limit comparison test. Okay, and all this is my answer here. Okay, and again, kind of the goal here is to get a solid answer. Okay, so here again, I take my given function, I get rid of all the extra stuff, and I'm just left with 1 over n cubed. So I'm going to choose 1 over n cubed. Okay, so same process, I take the limit as n approaches infinity. 1 over n cubed minus 2 divided by 1 over n cubed. So you end up multiplying. Okay, so you end up with the limit as n approaches infinity, n cubed over n cubed minus 2, which is equal to 1. Now again, I got a solid answer here. I did not get infinity, so I know that these functions are going to behave the same. I know that 1 over n cubed converges because it's a p-series, okay, with p greater than 1. So I can say that my given series, that's a 2, n cubed minus 2 also converges by the limit comparison test. Okay, so again, you might just want to take a look at the difference between some of these examples that I've done to see which one you would do when, but we can also talk about that in class. All right, that's it for today. See you later.